Yeah, so let's begin. Moving forward towards one of the most classic and foundational algorithm, we have the a priori algorithm. Okay, think about your daily routine where you open Amazon, Netflix, or walk into a supermarket. You'll see a recommendation engine which is suggesting you item. All these steps forms during a simple question, that is which item are frequently bought together. Okay, in the terms for the marketing place, this is called as market basket analysis. To formalize this, we use the association rule mining. Essentially, given a database of transaction, we'll see that if a customer buy item X, then what are the highly likely chances for him to buy the item Y. But we don't want to just find a random combination. Okay, so we have some of the rules for it, where we will be measuring some of the frequency and the strength known as the minimum support and the minimum confidence. The core matrix moving forward, we have support. This measure how frequently an item appears in the database. It's simply the number of transactions containing X divided by the total number of transactions. Second is the confidence. This is how conditional probability works. It answers that if given X happen, how often does the Y happen? Third one is the lift. This is very crucial because high confidence can be misleading. Lift tell us that if X and Y are actually independent or truly correlated. Okay, if lift is greater than 1, then it is positively associated. If lift equal to 1, then they are statistically independent. And if lift is less than 1, then they are negatively correlated. Okay, for the fourth one, we have the conviction. This measures the strength of the implication. It approaches infinity for a perfect rule. The formula for this is as given. Okay, so moving forward, we have a question that why we need such a special algorithm. If you have an universe of item I with just a few items, you can calculate each and every combination very easily. But what if the item grows? As the item grows, the search space blow up to exponential of big O 2 raised to power mod of I. So this is where we get the property of the downward closure and the anti-monotonicity that saves the day. The lemma states that every subset of a frequent item set must also be frequent. Equivalently, if an item set X is infrequent, then every single superset containing X will also be infrequent. Mathematically, the condition is given below. Okay, so now look at a lattice diagram. If item set E is found to be infrequent, marked in red, then we can instantly prune all of its superset which are marked in gray. Okay, if we don't, in this case, we don't have to either bother about counting them in the database. Similarly, if A and D is infrequent, subsets like AB, D, and ACD are instantly dropped. This drastically cut out the search space. Moving forward towards this section of the algorithm and the step-by-step example. So let's look at how this algorithm actually work. Phase 1, we need to find all the frequent item set using a level like breadth first search, or we can use another also. Second, we have extract the strong rules for those who have a frequent item set. Okay, moving forward to a concerned example, imagine we have 6 transactions and we set our minimum support threshold to 50%, which means that an item which must appear at least 3 transactions will be taken into account. Level 1, we'll take k equals to 1, we scan the database and count the individual item. We get our candidate list C1 equals to A subset 4, comma B5, comma C4 and D4. Since all the count are greater than equals to 3, then we mark all of them to frequent one item set list. Level 2 is keeping k equals to 2. We join the F1 with itself to create the pairs and scan the databases. We get the pairs as A, B3, A, C3, B, C3, B, D3, which passes our threshold. However, A, D and C, D only have a count of 2, so they failed and are filtered out. Moving towards third, we can see to join the frequency at a pair of 3 item set. When we are trying to evaluate A, B, D, we check its subset. Because we know A, D was infrequent in our previous step, we proved A, B, D immediately without scanning the DB. Only ABC remained, and with a support count of 3, it became the final frequent 3 item set. Now for the phase 2, we take a frequent item set ABC and break it down into rules. If our minimum confidence threshold is set to be 60%, we evaluate the rule like this. For B, A comma C, the confidence is 3 by 5, which is 60%. It barely passes, but the lift is only 1.08, meaning it is a weak correlation. Second, we have A comma C towards B. Confidence is 3 comma 3, 100% with a strong lift of 1.20. Okay, so here's an example which we have just solved. Now moving forward towards the complexity, application and the limitation. Let's talk about the performance. The biggest bottleneck of the algorithm is that it requires one full database scan per item level. If the database lives on a disk, then this is incredibly expensive. Okay, so moving forward, we have some of the alternate systems like the FP growth. While these algorithms use a generate and test strategy with many database scan, FP growth compresses the database into a tree structure called the FP tree, which require exactly two database scan total and the zero candidate generation. Despite of some of the limitation, the algorithm is being used in some of the fields like the medical diagnosis, web clickstream. For example, when we are using with the websites like the Netflix, Amazon, and other websites, then the bioinformation, evaluating complex gene expression pattern, then in also in the fraud detection part. Okay, so moving forward towards the end of this video, we'll see the outros and the key takeaways. Moving forward towards the end, we can have a quick reference that the a priori uses a level-wise BFS over an item set lattice using an anti-monotonicity to prune useless branches. Secondly, it used support to filter rare item set, confidence to the filter, weak rules, and always inspect lift to filter out the suspicious and the coincidental rules. Third one is for the massive and the industry scale. We'll look at FP growth in place of this a priori algorithm.